Hello, this is lab number 10, analyzing families of functions with calculus. Now what we are going to do in this lab is, we will look at one type of function which is called as the belts. You will know why is it called belts in very few seconds. And we will analyze this function for different aspects of it. So when I say different aspects, it means that how does a graph look like, what are the intercepts, what are the asymptotes, and so on and so forth. So we will look at them and then we will proceed. Now I've already created a MATLAB code which has got all the necessary information on it, so kindly stick onto it and then follow the same thing on your assignments as well. So let me open the MATLAB code. So here is the MATLAB code. So we have a function called belts. The reason is, if you plot that function, you would see a graph of that kind. But this resembles a shape of a bell. Now there are a few things that we must know prior doing this. One is that now here x is an independent variable, and we will look at this function for each positive values of c. Now c is a parameter, so that means that when you say there are different c's, you'd see different types of shapes that you see. That means as you change the parameters, you would see different approach to this problem. I mean, when I say approach, it means that analyzing functions for different values of that parameter. Now as I go that, so I am defining my variables x, c, and pi. You do not need to define pi, that is fine. And I'm assuming my c to be a positive number. As I told you before, c is a parameter, and I'm assuming that to be a positive number. Now I am assuming my x to be real. The reason is, if I don't assume my x to be real, you cannot imagine, I mean, if x is an imaginary number, that doesn't work well with the function. So we always want an x to be positive or a real number. I mean, a negative is also fine. So it has to be a real number. And my bell of x comma c, now this is a function of two variables, which is x and c, where x is an independent variable and c is a parameter. And that is the function. Now whenever you are given a function, out of curiosity, we always do this. As mathematicians, we always do this. One is that we always look how this function looks like when we plot it. Okay, so first thing I do is I look at the formula and I plug for different values of c to my bell function. Now see that I have three values of c, which is 1, 2 over 3 and 3. So I'm going to plug those and see how it looks. So that is my three different answers. Now you can use VPA and then check it, that is fine. I don't want to do it now with this. Then let's look at how to plot a graph. Now it's not new to us. We have seen this. We have seen how to plot a function, that is by using easy plot. Bell of x comma 1, that's going to plot the bell function for c is equal to 1. I'm switching on the grid and I'm holding on because I need to plot two more curves for c is equal to 2 over 3 and 3. So I'm plotting that. Within that interval, you can choose a random interval, that is fine. But whenever you choose the interval, you must see to that the plots that you have is all you can see. The interval cannot be too long or too short. You should see that these plots fit in a good window. Then I'm holding it off. So whenever you see a function, you always go and plot like that. Okay, now let's look at the intercepts of the bell function. Now each of the curve has a y-intercept at x is equal to 0. Y-intercept is when x is equal to 0, right? That means if that is the y line and that is the x line, y-intercept is for x is equal to 0. Now let's look at for different values of c and then also check for y-intercepts and x-intercepts. So that's what I do. I equate x is equal to 0 to get y-intercepts for different values of c. Okay, that's what I've done. So VPA bell of 0, 1, where x is equal to 0 and for all my bell function variable, and I'm fetching for different values of c. Say if c is equal to 1, 2, 3, 3, and in general for any value of c. So this is for any value of c. The answer that you get here is for any value of c. Plug in any c here. You should go back to one of these solutions. Say for c is equal to 1, you should go back to this solution. C is equal to 2 over 3, you go back to this solution. So this is a general case. You can plug any values of c. Okay. Now let's look at asymptotes. Now each of the function has a horizontal asymptote at y is equal to 0. Now you can clearly look at this picture. When y is equal to 0, that is on x-axis, of course on x-axis y is equal to 0, we have an horizontal asymptote. Now let's look at each one of them separately and then see if that is true. Now for that, what I do is I apply limits for the bell function for x tending to positive infinity and negative infinity. So that's what I'm doing here. Limit the bell function for c is equal to 1 for the variable x to positive infinity, and the same for negative infinity. And then limit bell function x comma 2 over 3. Now here c is 2 over 3 for x on both positive and negative infinity, and I'm repeating the same thing for x is equal to 3. Now I see to that if I limit x tending to positive infinity and negative infinity for any value of c, my answer is 0. That means I have a horizontal asymptote at y is equal to 0. Okay. Now let's look at extrema. I mean, that's the decreasing and increasing. We have seen this in our previous classes, that is on absolute extremum, that whenever you are given a function, you check maximum value, minimum value. Of course, we have seen this in, I think, lab 9 or lab 8. So we are doing the same thing here. How did we do that? Take the derivative of the function, equate it to 0, and then find the x value, right? So take the derivative, equate the derivative to 0 and find the x value, and plug that x value back to the function and see and you get a column of numbers where one among those is a maximum and one among those is a minimum. If this is not clear, please go back and look at the previous labs about maximum absolute extrema. So this is what I do. I mean, it's just the same as the absolute extremal syllabus. So that's not new to us. Now let's go to the next concept, that is intervals of concavity and inflection points. Now when under this, we always look at whether the function is concave up or concave down. Now if you go to this function, there is one more way of approaching this. We could always look up, say the function is concave up when the second derivatives are above the y-axis. Okay, so that's what I'm trying to do here. So what I do is I take the derivative of the bell function for a general case of c at x is equal to 2. Then I plot them. I plot each one of them. I'm plotting the derivatives here, and I see that this guy is concave up. Okay, so that's what I'm doing here. Now I'm repeating the same thing for different values of c, 1, 2 over 3 and 3, and I'm just looking and making sure that the plot what I see is within a suitable window. Okay, these intervals are random, so you can choose a good interval to fit the entire plots in a very good window. Okay, then for example, I'm just taking c is equal to 3, and I want to show you that if I take the derivative of the bell function for c is equal to 3, and if I solve for it, that is my answer. So that means that is the critical point. So if I go back and plug this, I should see the absolute extrema or minimum for c is equal to 3. Okay, so that completes this lab. I know this includes a lot of subsections, but it's not that hard. And if you look at lab assignment, Whatever we have done is just the same, but here you are solving for a different function. Now the last function was bells. Now here it is which of x comma c, and c is 1, 2 and 3 over 4, and the assumption is just the same. We are assuming c to be greater than 0 and s to be real and x to be real, and the other function is hill of x comma c for different values of c. Now it's just the same. What you have to do is change the function. Now previously we had bells, now here we have which and hill. Now change the function, and you have to analyze the function for c is equal to 1, 2, 3 over 4 for which, and 1.1, 2.1, 0.1 for hill function. Now previously we had 1, 2 over 3 and 3, but here we have different values of c. So you have to repeat the same procedure and find all the necessary information that we need, say formulas, graph, intercepts and asymptotes and all of these. Repeat the same procedure for hills and which, and replace c with the given c's on that is given here. Right? So that completes our lab 10, analyzing families of function. And I don't think it's going to be hard because it's just repeating the same thing that I've shown you. So yes, so that completes it. Have a nice day. See you next class. Thank you.